We're now going to talk about the hydrogen atom in relation to the ideas we've just been talking about for quantum numbers and in relation to explain the spectrum that we showed earlier. All right, so the Bohr model of the atom was something that Niels Bohr came up with quite some time ago, and it was before we understood all the nuances of quantum mechanics, but he had many of the same ideas, and it helped explain the hydrogen atom spectrum. Okay, so this is the Bohr model is for hydrogen specifically. And he understood the model of the atom to be that there is a proton in the center, in the nucleus, and for hydrogen there's no neutrons, there's just one proton. And then the electron had a choice of several orbits, he called them orbits, that went around that nucleus, and he labeled the orbits with numbers which were just like the quantum numbers, the principal quantum number n. Okay, so he named them as counting 1, 2, 3, 4 going out from the atom, from the nucleus, and he noted that whenever you excited an atom with heat or with electricity, that the electron would be excited to a higher n level. So the electron normally would be in the n equals 1 level, which he called an orbit. And when you excited it, you could put it in n equals 2, 3, 4, or higher. There are higher ones too. But once they were excited, they would immediately emit light and go back down to a lower level. And so he named these different groups. Well, we have names now for these different groups, and this is the Lyman series, the group that is all the choices where they start at a higher n level, n equals 2, 3, 4, or higher, and they emit light and they go back down to n equals 1. So that's the Lyman series. It always ends on n equals 1. Okay, so again, the electron emits light and goes down to a closer in orbit, which is analogous to the orbitals we've talked about. When they ended on n equals 2 level, like this group here, that was the Balmer series. So that ends on n equals 2. And when they end on n equals 3, that is the Paschen series. So that distinguished the different series that we saw in the spectrum earlier. And I'll go back up and show you that spectrum. Okay, so remember this spectrum. We have the Lyman series, we have the Balmer series with the Paschen series, and then we also mentioned what n level those lines represent ending on. Okay, they start at various n levels, but they end on, for the Lyman series, end on n equals 1. And so the different lines are all starting at different other n levels and going down or in to n equals 1. And same here, they start on whatever level and then they end on n equals 2. So the different lines are for starting at different levels. All right, so that is the hydrogen spectrum. Let's go back to where we were here. Okay, so the hydrogen atom is normally has an electron in an n equals 1 state. Okay, and we call that the ground state. So the ground state is the most stable, the lowest energy state, and that's the furthest in orbit. That's n equals 1. So if the electron's in that orbit, it is in the ground state. And any other state, n equals 2, 3, 4, or higher, is called an excited state. And remember, in hydrogen, there's only one electron. So it's in n equals 2, 3, 4, or higher. Okay, let's look at these in terms of energy. And let's also talk about some of the characteristics that Bohr noticed about the spectrum or about the certain characteristics he had for the Bohr model. He said only certain electron energy levels are allowed. Okay, so the different states, the different physical orbits also corresponded to specific energy values. And these, we called these orbits, we now call them orbitals. Because they aren't technically like orbiting, they're more of a smearing out of the electrons. Okay, and so the next part of his model was that as long as an electron stayed in one level, so as long as it stays in an n level, no light is emitted. But whenever an electron changes levels, then light is either emitted or absorbed, depending on whether it goes down or up in n levels. Okay, so when electrons change state, or change energy level, they can either absorb or give off light. Okay, so when n decreases, in other words, you go from like n equals 3 to n equals 2, then light is emitted. And when n increases, light is absorbed. Okay, and we can draw the energy level on a diagram with energy going up, and we can talk about the different n levels. We start with n equals 1 is always the lowest energy. The most inner orbit is the lowest energy, and we just number them going up, and they get all on top of each other, and they start piling up. The energy levels get closer and closer together as you get further out away from the nucleus, and eventually n equals infinity at what we call 0 of energy. Okay, so the lower levels are actually negative energy, which is more stable. All right, and so then anything that ends on n equals 1 coming from anywhere else is the Lyman series. And anything coming from anywhere going to n equals 2 is the Balmer series. And going from anything to n equals 3 is the Paschen. And these are all emission lines, because n is going down, and that's what we saw in the spectrum. All right, so then remember the Rydberg equation that had different n levels, and now we rewrite n equals 1 and n equals 2 as nf and ni. That's an I. And nf is the final n, and ni is the initial n value. And you can plug them in the equation and get all the spectral lines. All right, let's move on then to a new topic. So those energy levels explained the observed hydrogen spectrum, which I went over earlier. All right, so let's go back to the periodic table. Now that we understand quantum numbers, we understand s orbitals, p orbitals, d orbitals, and beyond, and talk about the periodic table. And it turns out that the periodic table historically was put together using reactivity and properties of the elements. So they were lined up into groups. Okay, they were put into different groups along the periodic table based on their properties, and different rows based on their properties. And then quantum mechanics came along, and it turned out everything fit. Everything fit together as it already was laid out based on properties. And the way that it fit together is that the outermost electrons in groups 1a and 2a were filling s orbitals. So that is called the s block. Groups 1a and 2a. And it turns out that groups 3A through 8A, were the outermost electrons in those were filling p orbitals. So this is known as the p block. And then the transition metals in between them were filling d orbitals, so they are the d block. And down below, the area that we put down below, lanthanides and actinides are actually filling f orbitals, so they are the f block. Okay, so quantum mechanics fit in what was already present for the periodic table. And finally, in this video, I'm going to talk about one more quantum number. Okay, we've talked about 3. We've talked about the principal quantum number, n. We've talked about the angular momentum quantum number, L. We've talked about the magnetic quantum number, m sub L. And these 3 together define an orbital. Remember, the principal number gives you distance from the nucleus, just like in the Bohr model. Further higher ends give you further out orbitals. Angular momentum tells you shape, SPD or F. And magnetic quantum number tells you orientation. Which way is that p orbital pointing, or that d orbital? Okay, but there's one final quantum number, which is the spin on the electron. And that is m sub s for spin. Okay, so there's a spin quantum number, and remember that n, l, and m sub l were always integers, whereas the spin quantum number is not an integer. Okay, m sub s can have one of two values. It can either be plus 1/2 or negative 1/2. Okay, so there's two choices for that. And basically, whenever you have an orbital, let's say it's an s orbital, you can have one of two different spins in that orbital. You can have an electron with a spin up, or you can have an electron with a spin down, and you can have only 2 electrons per orbital. All right, and that'll be it for this video.